Now let's do the second case. Did I, hang on a second, I want to make sure I know where I'm at. Okay, what about this one? What happens if I drill a hole in the top of the filter during backwash? So during backwash, this valve is open, the water is gushing out of this pipe and spilling, I guess, onto the floor and onto my computer at this water seal. And look at this. Look at what this manometer is telling us. It's saying that the water pressure right at the sand level is actually way down here. Is that a surprise? Why is the water level so low? Where would the water level be if I plugged a manometer, you know, into, well, look, the water is exiting into this little bucket at the bottom here.
Yeah, let me look around.
That free surface represents atmospheric pressure. And as we go up, the pressure has to drop, right? As you're going up in a swimming pool, the pressure drops. So as we go up, the pressure has to drop. And that means that the pressure inside the top of the filter is way below atmospheric pressure. Okay, cool insight about E-stars. So now let's drill a hole in the top of that filter. The pressure inside is actually way below atmospheric pressure, and the air is going to want to go, or the fluid is going to want to go from high pressure to low pressure. It's high pressure outside, it's low pressure inside, and so air goes in. So we're not going to actually drill any holes in the top of the filter, but I just wanted to make it clear that we're doing a very different thing when we switch between filtration mode and backwash mode in an enclosed stack rapid sand filter. In an open stack rapid sand filter, we manipulate the pressures by dropping the water level a really long distance in the filter box between filtration mode and backwash mode. The water level drops more than a meter in order to get the pressure lower at the top of the filter so that there's enough energy to actually back fluidize the sand. In an enclosed stacked rapid sand filter, we also change the pressure, but because it's enclosed, it's much easier. When it's operating in filtration mode, it's connected to an outlet tank that's at this kind of level. And when it's in backwash mode, its outlet is way down here. And so simply by opening up this backwash valve, we switch it so that it can access that new low water level, and the pressure like instantaneously drops. And we don't have to dump any extra water. We don't have that big chunk of water above the sand that we just waste. Here's a view of what all's going on inside the filter. So remember, we have a tall inlet box because that's where you get more and more head loss, more and more water level rise as the filter clogs. So that's happening inside here. That's where the clarified water is coming in through a hole in the bottom and then exiting through a bunch of pipes. So let's get rid of the outside of the tank. Okay, so I'm just deleting the outside tank so we can see what's happening inside it. So we can see all these, all the flow of water down into the 4 inlets, 1, 2, 3, 4, water coming in through this crazy system that includes water coming out of this pipe. So this is the water coming from the clarifier, comes up through this pipe, flows over the top of this, what I call a weir. It's the edge of the pipe. It flows over that edge of the pipe. And if you have multiple of these filters working in parallel, it's important to make sure that each of their weirs is at the same elevation, because that's what distributes the flow evenly between the filters. If the flow rate through your plant is low, remember we had a trick with the O-stars, the open stacked rapid sand filter, that we could open up a weir and get more flow to a filter so we could backwash it. Same thing is true here. Here we would just remove this, it's either a pipe stub or I believe it's a pipe stub. Remove this little pipe stub, and that will lower the elevation of that weir, and that will cause water that was going to the other filter to come to this filter instead. I'm playing with the idea of using a linear flow orifice meter here so that you can actually see what the flow rate is through the filter. The water is going through this linear flow orifice meter in reverse, in that it's going from the inside to the outside, whereas what you saw in the entrance tank, water was going from the outside, the entrance tank, into the LFOM and down into the flocculator. So here it's just backwards, but same physics applies. And then water comes back up out of three of these three pipes. And if you are filtering to waste, it goes down this line, which would be a waste line. And if you're not filtering to waste, you would plug a little pipe stub in there, and then the water would be forced down this pipe, and that would be your filtered water pipe. So those are the controls. They're like doing very, very similar things to what's happening in the O-stars. The advantages, it can be built in a factory. It's easy to add an extra filter to expand capacity. You don't waste as much water as you transition between filtration mode and backwash. There's no big flush of a lot of water above the filter. And this is one of the things that this is one of our projects at I Work How to Reach. We're still working on creating the design for this and developing the fabrication method so that this is relatively easy to assemble. So that's an ongoing project. A few more things about other challenges with stacked rapid sand filters. We started using slotted pipes, both for the inlets and the outlets. And if you think about this, the inlets are getting clarified water and they're injecting that into the sand. Clarified water has some flocks in it, so it's not entirely surprising that there might be some particles in that clarified water that could clog a 0.2 millimeter slot. And indeed, that happens over time, that the inlet slots would slowly clog. And so that was a maintenance issue because you had to take the sand out of the filter in order to access those pipes and then clean them. And so in 2015, we replaced those inlet slotted pipes with this wing system, which I've shown there, which has this inlet pipe with what we call a wing below it, and then there's orifices drilled all along the length of that pipe that the water comes out of. There's been this dream for years that we could replace the outlet slotted pipes with something similar. We haven't figured out a reliable method to do that yet. It's still worth doing more research to see if we can figure that out. The failure mode is that if anything happens that too much water starts flowing into the outlet, it's easy for it to fluidize sand and then carry sand into the outlet. And you don't want that because you don't want to lose sand through your outlet pipes and send it to your distribution system. So that is such an easy failure mode. We haven't figured out any reliable way to prevent that from happening. And so we are still using slotted pipes on the outlet pipes. A challenge is that there's, in O-stars, there's this big waste of water from that big flush that has to happen to get the big water level change. If we end up using our backwash recycle system, that ends up not being quite as big a disadvantage, but it certainly would be nice to not be wasting all of that water. And I want to also like make this pitch that, yeah, we've been playing with these filters for over a decade, and there's still a ton to learn. You think about rapid sand filters dating from, I don't know, right around 1900. So over 100 years of people using rapid sand filters. We've only been using these for a decade. There's still a ton to learn. And there's so many places where we just somewhat arbitrarily, but with some good engineering judgment, picked some values, and then we've stuck with them ever since, knowing that those cannot, it's not possible that those are the actual optimal values. So we have never experimented with changes in the filtration velocity, with changes in the sand diameter, with changes of the layer depth. All those things we kind of went with a reasonable value at the beginning, and then we didn't touch it. Clearly, unless I'm just have an amazing ability to roll the dice and get the right answer on the first try, none of those can be optimal. So there's lots of room for opportunity, lots of opportunity for more breakthroughs. Yeah, more research needed, which is why filtration research is one of the things that is happening at Ohio State. Okay, a few conclusions. Filters are really well suited for taking clean water and making it cleaner. They are not a good choice for treating slightly turbid surface waters greater than about 5 NTU. Meaning that if you look at the water and you see that it's too dirty to treat with a filter. They do remove particles and dissolved organic, the goal is to remove most of the particles and the dissolved organics using flocculation, flock filter, and plate settlers, and then you polish it off with the filter. Filter is the last thing you do after the water is already clean. A couple advantages of, that's pretty funny. I have written here 3, and it looks like that list is longer than 3. So it raises questions about my ability to count to larger numbers than 3. So 3 big advantages over rapid sand filters, and things come up in reverse order. Okay, so it's more compact, uses a smaller filter area. It's self-backwashing. You don't need to have any pumps. There's a single air valve that's used to control the whole system. So no big valves needed. It uses clarified water to backwash, and that clarified water isn't chlorinated, which means that the filters never see any chlorine, which means that the filters are biologically active. So this is biologically active filtration. We have not done any research on whether or not that's providing any added benefits for us, but biologically active filters do help reduce the dissolved organics a little bit further, and that's good. And we use hydraulic controls for the whole system to assure steady flow distribution between filters. And the more I learn about conventional water treatment plant design using mechanized system, the more I like this idea of just using simple hydraulic controls. Mechanized water treatment plants tend to have a lot of problems with getting their computer controlled system to provide steady flow through their filters. They're using computer controlled valves, maybe at the effluent side of each filter, to control the flow rate of water through each filter. And those mechanized valves easily oscillate. And so you don't get a nice uniform flow through the filter. And as you can imagine, if you have changes in flow rate through the filter, you tend to see poorer performance when you increase the flow rate, because some of the particles that had nicely attached, now when you increase the flow rate, the shear level goes up, and some of those particles get sheared off, and you end up with more particles showing up in the effluent for a little while. So steady flow is important. So rapid sand filters and stars filters require pretreatment with coagulant. And I just keep on saying this because I feel like it's a mantra that is so important. Sand filters cannot treat highly turbid water. It just doesn't work.